The inexorable law in mechanics is F equals m times a, the second derivative of x. In simple harmonic motion, force comes from the displacement x itself, F equals minus kx. Together, these two equations give the differential equation that describes simple harmonic motion.
That differential equation refers not only to a mass on a spring, but to any physical system that, when disturbed, is restored toward equilibrium with a force proportional to the disturbance. For example, the pressure of the air in an organ pipe, or the angle of a pendulum, the bending of a tuning fork, or the rotation of a clock movement. These systems and many others undergo harmonic oscillations. These oscillations can be too fast to see, at least under normal circumstances, or too slow to wait for. Or they can be any other frequency, high or low. No matter the frequency, however, they can all be described by the same differential equation. The differential equation is solved by the time-honored technique of guessing. A long time ago, someone guessed that the solution may be a sine function. It was an educated guess, because the motion of a mass oscillating on a spring resembles the motion of the shadow of a particle moving in uniform circular motion. So the idea of guessing a sine function seemed quite natural. In this case, a sine function with amplitude A and angular frequency omega. But if that's x, is its second derivative equal to minus k over m times x? The answer is yes, if omega is chosen correctly.
For the mass on a spring, the angular frequency is equal to the square root of k over m. The stiffer the spring, the higher the frequency. The greater the mass, the lower the frequency. But whatever the frequency, it depends on the mechanical properties of the oscillator, such as the mass and the spring constant. The time needed to make a complete cycle does not depend on how big the swings are, represented by A in the equation for x.
So even as the oscillations die down, harmonic oscillators continue to keep perfect time. The frequency is measured in radians per second. There are 2 pi radians in each complete cycle. Likewise, in the great clock in the sky, each cycle is divided into radians, as if the universe were an enormous circle. To an extent, it is. The natures of uniform circular motion and simple harmonic motion are closely related. Each clock, in its attempt to duplicate the cycles of nature, is a mere shadow of the cosmic clock. Just as uniform circular motion and simple harmonic motion shape up much the same in nature, the potential energy of harmonic motion can be visualized as a curve shaped like a bowl. Why this shape? Because of the force law and the definition of potential energy. ball starts out with some potential energy. As it rolls toward the bottom, the potential energy changes to kinetic energy. As it rolls up the other side, the kinetic energy changes back into potential energy. Over time, there's a continual interchange between kinetic and potential energy. But even though both the potential energy and kinetic energy are always changing, the total energy is always constant. When any harmonic oscillator is disturbed, the disturbance produces a force that pushes it back to where it was. There, the force is zero, but inertia keeps it going until the reverse force stops it and pushes it back once again. This is the essence of harmonic motion. A simple harmonic oscillator. If it were really simple, it would go on forever. A perpetual motion machine.